What do physicists really mean when they claim that something is an illusion? It's a fascinating question, one that often arises from an analogy with optical illusions, a concept we're all familiar with. Consider the cafe wall illusion, also known as the Münsterberg illusion. Here, rows of alternating dark and light bricks are separated by perfectly parallel lines. Yet, when we glance at it, those lines appear to be sloping, bending, almost dancing before our eyes. It's a geometrical optical illusion, one that teases our brains into seeing something that isn't there. But again, the illusion doesn't negate our perception. It is precisely what we perceive, even if it's not the truth of the matter. And in physics, when we say something is an illusion, we are often speaking to this very experience. A phenomenon might look like one thing on the surface, but when we dig deeper, it reveals a more complex, sometimes counterintuitive nature. Take, for example, the famous Fraser spiral. At first glance, it undeniably appears to be a spiral, a twisting, turning path that seems to lead somewhere. But look more closely, and the illusion unravels. What you're actually seeing are concentric circles, perfectly arranged to trick your brain into perceiving a spiral. This is the power of an illusion. It is something we see, something we experience as real, but only as long as we don't scrutinize it too closely. The moment we do, the illusion dissolves, revealing a different reality underneath. Now, when physicists speak of something being an illusion, they are often pointing to a similar phenomenon in the natural world. Something might appear to be one way, solid, continuous, or even intuitive, but under rigorous analysis, it turns out to be something else entirely. The illusion in this context is not about deception, but about the layers of reality that are hidden from immediate perception. This brings us to the solidity of matter, a concept that feels so fundamental, so real, that it's hard to imagine it as anything but the bedrock of our sensory experience. When we touch a table, lift a rock, or hold a cup, they all feel undeniably solid. And yet, if we delve into the fabric of matter, we find that it is composed almost entirely of empty space. The atoms that make up these objects are mostly void, with tiny particles, protons, neutrons, and electrons, dancing in a vast emptiness. So is solidity just an illusion? In a way, yes. But that doesn't mean the experience of solidity is any less real. It's an emergent property of how our senses and our brain interpret the interactions between particles. The illusion of solidity is as much a part of our reality as anything else, but it also invites us to explore the deeper layers of that reality. Now let's talk about free will, one of the most profound and deeply personal illusions we experience. Many of us feel with every fiber of our being that we are the authors of our actions, that our decisions are ours and ours alone. This feeling of autonomy, of exercising free will, seems so real, so integral to our sense of self. Yet, when we probe into the workings of the human brain, the story changes. Neuroscience suggests that what we perceive as free will may be nothing more than the inevitable outcome of particles and neurons following the laws of physics. Our choices, it turns out, might be predetermined by processes we're not even conscious of, decisions made before we are aware of making them. So, is free will an illusion? In the strictest sense, perhaps. But even if it is, the experience of free will, the feeling that we are in control of our choices, remains profoundly real to us. If you're intrigued by this concept of free will as an illusion, you can explore it further in the video linked in the description. It's a topic that not only challenges our understanding of the human mind, but also touches on the very nature of what it means to be human. Let's delve into the enigmatic nature of time, one of the most perplexing concepts in both physics and philosophy. We all experience time in a very visceral way. It flows, it marches on, it seems to carry us from one moment to the next. But what if this sense of time's passage is nothing more than an illusion? It's a provocative idea, and one that has sparked endless debate among physicists. You see, time is at the heart of a profound and ongoing controversy in the world of physics. In Einstein's general theory of relativity, time isn't just an afterthought, it's woven into the very fabric of the universe. Time is treated as a coordinate, intricately linked with space to form what we call space-time. This is the foundation upon which general relativity is built. Time and space are two sides of the same coin, inseparable and equally fundamental. However, in the realm of quantum physics, time is something of an outsider. Unlike space, time in quantum mechanics doesn't play by the same rules. For instance, you can pinpoint where a particle is, but the question of when it is there becomes much murkier. This distinction creates a tension between the two pillars of modern physics, general relativity and quantum mechanics, that refuse to neatly align. This disconnect is what physicists refer to as the problem of time. Why does this matter? Well, this clash between the two theories is more than just an academic curiosity. It's a central obstacle in our quest for a theory of quantum gravity, a unified framework that would seamlessly integrate the principles of quantum mechanics with those of general relativity. The problem of time is a major piece of this puzzle, one that has stymied physicists for decades. So how do we reconcile these conflicting views of time? One of the most promising approaches is to make time relational. In this framework, the passage of time for any given object isn't an absolute, standalone phenomenon. Instead, it emerges from that object's interactions with other objects. This relational view of time has the potential to harmonize the different roles that time plays in general relativity and quantum mechanics. In general relativity, space-time is a smooth, continuous fabric, but it's not something we can directly measure. What we actually measure as time comes from clocks, and in the language of physics, a clock is anything that ticks with regularity, marking the passage of time. Now, applying this concept to general relativity is relatively straightforward. By calculating what physicists call proper time, you can link the ticking of a clock to the fabric of spacetime. But when we turn to quantum mechanics, things get trickier. How do you define a clock in the quantum world, where particles exist in states of uncertainty and superposition? And once you have that clock, how do you derive a concept of time that makes sense in the quantum framework? This challenge has driven some of the most exciting recent developments in physics. A significant breakthrough was made with the publication of a paper titled "Magnetic Clock for a Harmonic Oscillator." The researchers behind this work used a quantum clock, a simple harmonic oscillator, as a means to define time for another quantum system entangled with it. The key here is entanglement, a uniquely quantum phenomenon where particles become deeply linked, such that the state of one directly influences the state of the other, no matter the distance between them. By leveraging this entanglement, the researchers demonstrated that it's possible to establish a sense of time in quantum mechanics that can correspond to our classical understanding of time in general relativity. The implications of this are profound, as it offers a potential bridge between these two seemingly incompatible theories, bringing us one step closer to the elusive goal of a theory of quantum gravity. In essence, what we're grappling with here is a deep, almost philosophical question. Is time a fundamental aspect of the universe, or is it a byproduct of our interactions with it? And if time is indeed an illusion, what does that mean for our understanding of reality itself? The answers are far from settled, but the journey to uncover them is nothing short of extraordinary. What's truly groundbreaking about this recent document is that it extends these findings beyond the microscopic realm. The researchers have demonstrated that this approach to defining time through quantum mechanics doesn't just apply to tiny particles. It holds true even when the other system involved is large. This breakthrough could very well serve as a crucial link between the seemingly disparate worlds of quantum mechanics and general relativity. If this is indeed the mechanism by which time emerges in the quantum realm, it forces us to ask a profound question. Is time, as we experience it, nothing more than an illusion? In a very real sense, the answer might be yes. What this suggests is that, at its most fundamental level, the universe doesn't possess time as an independent entity. Instead, what we perceive as the passage of time is merely the result of relationships between different things in the universe. It's not that time is ticking away as you watch this video. It's more accurate to say that the progress bar you see on your screen is merely correlated with the ever-growing number of social media notifications waiting for you to check them. And let's be honest, we've all suspected that was an illusion anyway. But before we wrap up, let's remember that these questions about time aren't just academic. They strike at the heart of how we understand our place in the cosmos. So thank you for joining me on this exploration. If you found this intriguing, don't forget to like, subscribe, and share your thoughts in the comments below. Together, let's continue to unravel the mysteries of time, one step at a time. Stay curious, stay kind, and always remember, we are all interconnected, not just in space, but through time as well.